At this point, you should be done with labs 8 and 9, and while you're watching this particular lecture, you could do lab 10, which is all about spectroscopic binaries. And after this lecture, you'll be done with the Unit 3 material, and there will be a checkpoint, number 6, for Unit 3, and you can finish up homework number 2 for Unit 3, and then you can tackle the Unit 3 exam. Now, to understand spectroscopic binaries, the first thing that you need to do is understand the Doppler effect.
I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Hi, Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Now, that second example wasn't so great, but the first one with the train going by, you should have heard it go with a little bit more epicness than that. Anyway, when we have waves, like sound waves, that are coming from some kind of a stationary object, then that object is just sitting there, the waves are going out in every direction, and no matter where you stand, if you stand in front of the object, behind the object, off to the side of the object, you will always measure the exact same wavelength, which will be that lambda that's given there in something that looks like an upside down Y. Now, when things are moving, the story is a little bit different. You can see as this thing moves to the right, it's still emitting waves at the same frequency, but the problem is it's actually catching up to its own waves as it moves to the right, and it's leaving behind its own waves that are off to the left of it. And so if you happen to be standing in front of this object, then what you're going to measure is a wavelength that's a little bit shorter. If you happen to be standing behind this object, you'll be measuring a wavelength that's a little bit longer. With sound waves, something that's got shorter wavelengths sounds like it's a higher pitch, and something that's got longer wavelengths has a lower pitch. And so you get the sound with the high pitch going down to the low pitch as the thing passes you. But light doesn't have a high pitch and a low pitch. What it does have, though, is wavelengths. So of the light that you can see, which color has the shortest wavelength? And which color has the longest wavelength of the light that you can see? I've got a little diagram here that's got two stars that are orbiting around a common center of mass. So this is like a little binary star system. And it's got stars A and B. And star A happens to be a blue star, and star B happens to be a yellowish star. And you happen to be over there where that little clip art telescope is. So, from your perspective, from where the telescope is star A moving towards you, away from you? Or do you need to know some other information before you can answer this question? The little arrows, by the way, indicate that's the direction things would be moving once they got to that point. Now this is where it gets a little bit trickier. When you're looking at star A, as you realized in the earlier question, it's moving away from you. So if it's moving away from you, what sort of wavelengths is that going to have compared to the wavelengths that you'd get if the thing were sitting still? Is it going to have spectral lines at wavelengths that are longer than it would when it's sitting still? Shorter? Does it depend on how far away star A is? Does it depend on which wavelength you're talking about? What about star B? At this exact same instant in time, what will its spectral lines be doing? So if you know that with sound waves, anytime something's moving away from you, the light is going to be shifted to the longer wavelengths, then for light, what does the relative motion away do to the light wavelengths? Does that make them towards the red or the blue? Similarly, if you've got something that is moving at you and you've got sound waves coming off it, then what you'll get are sounds that are higher pitched and shorter wavelengths. So if you're looking at light instead, if you've got relative motion towards you, what does that mean about the light that you're seeing? Is that going to be shifted to the redder or the bluer wavelengths? So here are the answers. Anytime you've got relative motion away, and what I mean by relative motion is the distance between these things is getting greater. It doesn't matter which one is doing the moving, or they could both be doing the moving, so long as the space between them is becoming bigger. So anytime you have relative motion away, the light is going to get shifted to the redder wavelengths. It's going to be red shifted. And anytime you've got relative motion toward, and again, it doesn't matter which object is doing the moving, so long as these things are coming together. It could be both objects moving at each other. All you need is that there's relative motion toward. And whenever that happens, you get the light shifted towards the bluer wavelengths. It's blue shifted. I'm about to show you some screenshots from these interactive ranking tasks that are on this website. And what I want you to do is take a look at it and ask yourself which stars or which star is moving towards the observer. Which star or stars is moving away from the observer. Which stars are moving the fastest? What will the motion do to the wavelengths of the light? Will it make it red shifted or blue shifted? Now, one of the things that I haven't mentioned so far is that the faster something is moving, the more that shift will be. You can hear it in race cars, but you can't really hear it with just your basic car going down the street, right? I mean, you watch NASCAR and you get that kind of sound. But if you're just standing on the corner of Winslow, Arizona, and some car goes by about 20 miles an hour, you don't hear that same thing because the Doppler effect isn't so great. So, whenever you have motion toward, you get a blue shift. If you have fast motion toward, you have a big blue shift. Whenever you have motion away, you'll have a red shift. Whenever you have fast motion away, you'll have a really big red shift. One thing you need to remember is that on this particular website, there's a little book icon, and if you ever get confused, you can just click on that and it'll give you some information. So here's a screen grab from that particular interactive, and right here you've got stars A, B, C, D, and E. Now notice that the stars are different colors. But remember, what does the color of a star tell you? It doesn't tell you about its motion. They don't move that fast. What you can see, though, in this is that you've got a couple of stars that are moving away from you, a couple of stars that are moving towards you, one star D that doesn't really seem to be doing anything except for moving across your line of sight. And the thing is, whenever something is moving across your line of sight, at that instant, it's not moving away from you, it's not moving towards you, it's just moving kind of at a 90-degree angle to where you're looking, then that's one of those instances where you will have no red shift or blue shift. There will be no shift. The thing has to be moving at you or away from you. Now, if you look a little bit later, it'll be different. But at this instant in time where you've grabbed this motion, it's not coming at you, it's not going away from you. And so it wouldn't have any blue shift or red shift. Things that you have to really keep in mind for this part of the class is that the color of the star does not tell you about its motion. Because remember, the color of a star tells you its temperature. Even though you did that interstellar reddening thing, that really doesn't change the overall picture for things, right? A reddish-looking star is still a reddish-looking star. So the color of a star tells you the temperature. But what you're going to be looking for to find out if things are blue shifted or red shifted are these very, very teeny tiny subtle changes in where the spectral lines are. So for instance, you're trying to find the hydrogen lines in something. It's supposed to be at 6,378 angstroms for the H-alpha line. 6,378. Now a really zippy star might have that at 6,380. You're not going to see that visibly. You would have to really stretch out the spectrum, really have a clue about where all the wavelengths are exactly, and then you'd be able to measure something like that. So you're not going to look at a yellow star or a blue star and go, oh, hey, those must be moving at me differently or something. Okay? If it looks yellowish, it's because of its temperature. If it looks bluish, it's because of its temperature. If it has 5 points, it's because it's clip art. Another thing that is super important to keep in mind is that it doesn't matter where these objects are. It does not matter how far away something is. The only thing that matters is the relative motion between the object and observer. That is the only thing that matters. The two stars pictured here have exactly the same blue shift. It doesn't matter that the yellow star is farther away. If it's moving at you at the same speed, it's going to have exactly the same blue shift. So, just bear in mind, anytime that you've got relative motion toward or away, you're going to have a Doppler shift. With a train passing by you, or a race car passing by you, or a binary star system where maybe one star is coming at you and another star is going away from you at the exact same time. Doppler shifts only tell you about the relative motion. And remember, the color of the star does not tell you the speed or the direction of motion, it just tells you the temperature. What does tell you the speed is how much the lines, the spectral lines, are offset from where they should be. So, here's the Dr. Seuss book that your mom probably didn't read to you. Red shift, blue shift, red fish, blue fish. This fish is moving fast. This fish, never mind. At this point, get out your lecture tutorial book and do the lecture tutorial about Doppler shifts from page 75 to 79. Right now, just questions 1 through 10. There's a lot of stuff in here, and I want you to remember your mantras because there's going to be a time that you're going to start to doubt your mantras or you're going to forget them. So anytime you see something about the color, remember, recenter and tell yourself the color of a star tells you its temperature. And if you see something that says something about the distance to things, remember, hey, that doesn't change the Doppler shift. The only thing that matters is the relative motion. So, when you're looking at page 77, look at the spectra at the bottom of that one. Which star is moving the fastest? Notice that this question isn't saying which star is moving towards you, nor is it asking which star is moving away from you. It's saying which one is moving the fastest. And to figure out which one is moving the fastest, what you would do is you would look for the spectrum where the spectral lines are offset the farthest from where they're supposed to be. And one of the examples gives you a star that's sitting still. And so that tells you this is where these spectral lines are supposed to be. So you need to find the spectrum that has the lines the farthest away from that. Now look at the chart on page 78 of the lecture tutorial. And you've got a number of stars, and there are wavelengths associated with a particular spectral feature on them. And this gets a little confusing sometimes because people aren't sure, well, what does this mean? It's supposed to be at 656 nanometers. That's your H alpha line. Astronomers would say it's 6,563 angstroms, but whatever. Anyway, it says 656 nanometers, and that's where it's supposed to be. Now, if something's coming at you, then it's going to be blue shifted, which means everything is going to be shifted to shorter wavelengths, which means that anything that is a shorter wavelength than the 656 will be moving towards you. And if something has a wavelength that is way, way off from 656 nanometers, and it's a smaller number than 656, then it's moving fast towards you. And all of that stuff that I just said in the opposite sense will give you the redshifts and the things that are moving away from you. So look at those stars and figure out which one is moving the fastest towards us and which one is moving the fastest away from us. That entire set of lecture tutorials was about single objects that are moving at you or moving away from you. But let's back up to where we were originally, which was with binary stars. So we've got a view of a binary star system at 3 different points in time. In the first place, you've got star A coming at you and star B going away from you. And in the second panel, you've got stars A and B both kind of crossing your line of sight. And in the third panel, you've got star B coming at you and star A going away from you. So what you would see originally is that A's spectrum goes from being blue shifted to not having any shift to being red shifted. And star B starts out as being red shifted and then not having any shift and then being blue shifted. So here's an animation that shows you the binary star system as seen from above, as well as the spectrum that you would see if you got to look at this thing from the side. And so you've got the 2 stars going around each other, and what you'll see are spectral lines that start out together, separate, come back together, and then separate, depending on where these things are in their dance. So I guess this could be dancing with the stars. So here are some real spectra from a real object called HD 80715, which is the 80,715th entry in the Henry Draper catalog that Annie Cannon and all of those other Harvard computers worked on way back in the 1880s through the 1920s. Anyway, what you've got in the upper left is what the spectrum would look like at a time of 0.061 days. So basically at the beginning, this is something where you only see one spectral line. And as you see, as time goes on and you go down to 1.338 days, you've got 2 spectral lines that are definitely separate from each other. And then you keep on going through time, and by the time you get to 1.886 days, the spectral features have come back together and merged. And then you go through time some more, and then they split again. And then you keep going through time, and you get down to that bottom right panel, and it looks like they're about to merge again. So, looking at this, what is the orbital period for this particular spectroscopic binary? You don't have to compute it down to the last decimal point. All I want to know is, do you think that it's a little less than a day, 2 days, 3 days, 4 days, or what the hell? For that last slide, I'll give you a little bit of a hint. When it starts out, you've got the 2 objects that are both crossing your line of sight. And then they will cross your line of sight again a little bit later. But at that point, have they completed an entire orbit? Anyway, so here we go. Binaries. Why did we get onto these things about binary stars? Remember, things that orbit other things follow very specific rules. And the orbit is based on gravity, which is dictated by the separation of the stars and the masses that are involved. Which means that if you know the orbital period, how long it takes for these stars to move around their common center of mass, and you know their separation, then you can go through that little equation and you can solve for the masses of the stars. And originally you get the total mass, But all you have to do is see which one moves more to figure out the individual masses, like the fat uncle small cousin example, or like the little Play-Doh on a dowel example that you did for your lab. And once you get done sorting all of this stuff out, what you find out is, amazingly, for the main sequence stars, the spectral type is also related to the mass, which is really convenient because we already knew that the spectral type was related to the luminosity. Now we find that the spectral type is related to the mass for main sequence stars. The lowest mass main sequence stars are the M types, the M9s, and they can get all the way down to 0.08 solar masses. That's a 1/12 of the mass of the sun, and that is as low as you can go and still be a star. Now, the O-type main sequence stars can be as massive as 60 times the mass of the sun, or even 150 to 200 times the mass of the sun. Problem is, once you get to masses like that, you've got all this energy that's pumping out from the core, and it literally takes your star apart. There's a record holder right now that had 300 times the mass of the sun when it was born, but apparently along the way has shed about 20% of that. Here's an HR diagram that has, among other things, the masses listed for some of the stars. So you look down there on the red end of the main sequence and you see a little purple thing in there that says 0.1 M sun. And then at the very top of the main sequence in the blue you see this thing that says 60 M sun. One of the problems that I have with this particular HR diagram though is that it kind of gives you the impression that Betelgeuse is just a little bit bigger than the sun, when it is in fact like 1,000 times bigger than the sun. So they didn't really do a stupendous job of giving you the relative sizes here, but there are these little diagonal lines that are cutting across. From the bottom left it says 10 to the -3 solar radius there. That means that anything along that line is 1,000th the radius, the width of the sun. And as you go up to the very top there next to Betelgeuse, you're up to things that are 10 to the 3rd solar radii, which is 1,000 times the width of the sun. I realize that that seems like an awful lot of information because you did Doppler shifts and you did spectroscopic binaries and you figured out stellar masses all in this one lecture. But the good news is you're done with Unit 3. The bad news is stuff's about to get really weird in Unit 4. But before it gets really weird, go ahead and finish up your Unit 3 second homework set and your Unit 3 Homework 2 quiz, and you've done all of the various labs. And when you've digested the material from all of these lectures, go ahead and take your Unit 3 exam. You can open Unit 4, but not any earlier than 12:01 a.m. on the 15th of June. And remember, email, Facebook, discussion board, 1-minute papers, any questions that you might have.